video, I am going to explain about dual mode operation, one of the unique feature of every operating system. So in this video, I am going to cover this and other topics. First, I will explain what do you mean by kernel and what do you mean by bootstrap code and what this code will do. And then I will explain what is interrupt and trap, and finally we will explain this dual mode operation. Suppose if you are good in these topics, you can skip this and directly you can go to this topic, okay? And so if you like this video really, please like this, and if you not yet subscribed, please subscribe to the video and share among your friends, okay? Thank you in advance. Okay, let us see what are these topics one by one. We know that we users, every type of files we are storing in the secondary memory. That we know that. Already explained in my previous videos. That means whatever the file, it may be the file, maybe the movies, it may be the games, it may be the songs, it may be some Word document, it may be PDFs, it may be Excel files, it may be some softwares, whatever the type of files, generally that we stored in where? We stored in the secondary memory. That means we user stored everything in the secondary memory. That means every file means including our operating system also. Most of we are using Windows, right? Some people also use Linux or Unix or Ubuntu, that other operating systems also. That the operating system also, let us say Windows, so they also store this Windows in the secondary memory, right? And I told our processor, our CPU can take only from what? Main memory. Main memory, it never takes from the secondary memory. So, but whichever the program we want to execute, first we need to move into the main memory. Now, first I have to move to the main memory. But now the question is, what is the size of the Windows, whatever we are using the Windows 10? So, this is some 15.5 or 15.6 GB. But what is the size of your overall main memory? Hardly our main memory is 8 GB, 4 GB or 8 GB RAM we are using. So this is your RAM. Okay, so is it possible to fit that 15 plus GB into this 4 GB or 8 GB? No way. Then how we can run? I told for every computer system, compulsorily one software should keep running, and that should be our operating system. That means no computer will work without the operating system. So operating system is a system software which should keep running. But it is not possible to fit this 15 plus GB of data into this 4 GB or 8 GB. Then what is the problem? How it will run? So for that, what we will do, instead of moving the entire Windows operating system or any operating system, so we are moving only the essential part of that operating system. We call core part. Okay, we'll call it core. That is very important. Core part or essential part of the operating system, and that should be there in each and every system in order to run. So suppose if I say our system is functioning properly, means says it is working means, so that essential part of the operating system should be keep running, and that is called what? Kernel. So kernel is the essential part of the operating system which should be keep running in our system in order to make any user task. That means, so there's a kernel. So we know what you mean by kernel. Okay. So now next thing is bootstrap code. So now I told initially this is we stored in the secondary memory. But I told in order to run this, somebody has to move this code into the memory. Who is going to bring? I told in my first video, it will be bring by what? It will be bring by our operating system itself. Operating system itself. That is how kernel bring itself. Not possible. So what they will do? So there is a separate program called bootstrap code. Okay, bootstrap, BS code, bootstrap code, and this code is a very small program, and it will be stored in the read-only memory. In the read-only memory, and this read-only memory is directly connected to our processor, and both are on the motherboard on the fixed slot. And there is a hardware circuit which connects CPU and this bootstrap code. Whenever we system on, whenever we switch on our system, the first program now, our CPU will go to that read-only memory location and get this bootstrap code, and it will load it into the main memory and it will run first. Once now in main memory I am having what? Bootstrap code. Now once I load, now this bootstrap code is running. Now what this code will do, this code just contain the address where this kernel part of the operating system is stored, and it will go to this main secondary memory, get this kernel part, and it will bring. So that is what I told this one. So once our bootstrap code bring this kernel part into this one, now both the kernels are working. So now once this kernel is executing, then only the user can do any task. See, till that, see, whenever we switch on the system, we cannot do anything immediately unless our kernel will start getting executing. Once our kernel is loaded and start executing, then user can do any task. So that is the concept. So hope you understand. Now the summary is, when we switch on the system first, okay, switch on the system, so both kernel and the bootstrap code both are running in the main memory, both are there in the main memory. That is the concept what we need is, okay. So summary is, whenever we switch on the system, so both bootstrap code and kernel is running. Once these two are settled and running, then only user can do open any file, run any other user program. Okay, till that our computer system is waiting. That means once our system is on, we have to initiate something. That means we need to do some event. That means either we need to open some file unit or we need to open the Chrome. That means user has to initiate. Until user is initiating some task, our operating system is keep waiting, because it's nothing to do. It doesn't have any process to execute. It doesn't have any IO devices to service, or it doesn't have user request to provide. Okay, so it is waiting for some event to occur. So once user initiates, then only it can start. Okay, that means our operating system, our CPU is waiting for event to occur. And in all our modern operating systems, events happens in the form of interrupt. So that means all our modern operating systems are interrupt driven. We'll call this as an interrupt driven. Now let us see what you mean by interrupt. Okay. See, these interrupts are nothing but a hardware signals generated by the IO devices, either by the input devices or by the output devices to the CPU. Okay, these interrupts are what? Hardware signals generated by whom? IO devices. To whom? To the CPU. For what purpose? In order to indicate I am ready for so and so data transfer. Suppose, assume now, once our system is on, user types something. So that means user types something means he entered some data that through the input device. Now input device is having some data. That input device wants to give to the processor. That means input device having some new data. So it has to inform CPU saying that I am having some new data, come and collect. So how it will inform? Through a dedicated one control line called interrupt request signal. Okay, so that hardware, similarly output devices. Whenever output device is ready to display anything, okay, at that time that will send again a signal to the processor saying that I am ready to receive any data. So like that, whenever the hardware devices, especially what? IO devices. Whenever IO devices are ready for data transfer, these IO devices informs the processor saying I am ready for some IO data transfer. That information is go through one signal, one separate wire in the control bus. Okay, so the hardware signal generated by the IO devices to the CPU indicating for ready for IO data transfer, that signal is called interrupt signal. Okay, this is by hardware signal. Similarly, we have software signal. See, generally user will do tasks through programs. Whenever user want to make processor to do some task, user writes some program and that program will be given to the processor. Now processor runs this program. The programs may contain some of the errors. Sometimes our programs also need CPU attention or our user attention. Suppose there are some errors are there. Now it has to display to the user saying that in so and so locations of the program some errors are there. Now once user came to know that the errors about the program, user come and debug that and again fix and again run. So traps are nothing but the hard software signals generated by the programs because of the errors present. Okay, so that's what the trap. Okay, trap is nothing but software signal generated by the programs. Okay, so there is a trap. So we know the trap also. So now we know that in our random access memory, RAM, both bootstrap code and as well as kernel, both are sharing the same main memory. And almost 50 to 55% of our main memory is loaded by bootstrap code and some kernel and some essential system software. And remaining almost 50% of our data or RAM space will be available for user program. So assume once our system is get on after loading all these things, assume user open the Chrome. Okay, Chrome. That means now assume our Chrome is also running here. Chrome or whatever the browser, some browser is running. After that, user opens some app. So that is also app 1, it is okay. App 1, that is one application. App 1, that is running. So like that, assume user opens some 2-3 files and all are there in this main memory. Now that means our in main memory, both, see these are the system software, okay, system programs and user program, both are sharing. What is the problem then? When both are sharing, any one program, either maybe user program or generally user program only. A one user program may harm other user programs or it may harm our operating system also, that is a kernel. Suppose if our data present in one program, user program, if it harms or damages the hardware or the kernel, then our operating system going to get crash, our system get crash. So for that, we need, our operating system has to make sure that which program is executing, whether it's user program or system program. So why it needs, see, suppose since we are doing multi-programming, multiple user programs are executing at the same time. When multiple programs are executing, any one user program should not damage or harm other programs, especially the system programs. Suppose, assume there are 5 programs are running, user programs are running. If any one, so due to any one error present in the any one user program, that will harm the operating system. Now, how to identify who has did this one? For that, what I have to do? Now, I don't know which program has really did this damage. So, at that time, we need to suspect all the 5 programs. Suspect all the 5 programs means what? We need to check the entire program code where something is wrong is happened. We need to check. Is it possible to check all the programs? No way. So it is not possible. That means it is not possible to suspect all the programs. Okay, suppose. So, okay, it is not possible to suspect all the programs. In thinking in that way, if you are allowing any one program to execute, that is another solution is what? We should not run more than one program. We should run only one program at a time. So, if you do like this, then suppose if anything is happened, you can surely say this user program only did that. This is how we came to know. But what is the problem if you run only one program? We cannot do what? Multitasking. But nowadays we are using multitasking programming because we user wants to run too many programs at the same time. So multitasking cannot be happen. So these are disadvantages. So to make sure that which program is running, so that's why our operating system is not allowing user program directly accessing the hardware. In my first video, I told user cannot access the what? System. That means system hardware means what? It may be CPU, it may be IO devices, or it may be a memory. That means main memory. But user cannot do operation directly on our hardware. So we need what? In between, operating system acts as an interface. Okay, that's what operating system is. That means this is not allowing user directly to work on this because it may do that. That means user program may do some damages on the hardware. So that's why it is not allowing. So wait, understood why it is not allowing? That also we discussed in the first. Now also discuss more technically now. Okay, now. So when we are running multiple user programs, so in order to make sure that which program is executing and which program is running on the hardware, so every operating system provide one operation called dual mode operation. That means two mode. Dual means two. There are two different modes are there. One is user mode and another one is kernel mode. These are the two modes. That means if user program is just needs CPU, it doesn't need any IO devices. So simply if the user program is running, at that time we'll say our user program is running in user mode, it doesn't need any IO devices. Whenever our user program wants to get some, because in every program we are taking some input values and we are printing some values. If you take in C programming language, we are using printf and scanf for reading and printing. If you take in Java, we have the system.out.println. We are using the statement every program. That means in every program we are printing something. That means we need output device. And in every program we are accepting the input at the runtime. That means we are using input device. That means every user program needs some services from the IO devices. Whenever our user program needs IO devices, now it is not allowed. So it has to inform operating system saying that I need IO device services. When it will inform, how it will inform? Through a call called system call. So our user program contacts operating system to get the IO devices. Now it has to use some program and that is called the system call. Okay. Now through system call, our user program communicates operating system. Now on behalf of our user program, operating system works on or take this code and works on these IO devices, get the service on it. That means actually operating system is working on these IO devices, but on behalf of what? On the user program. So when operating system is working on the IO devices on behalf of our user program, then we will say our user program is running in the kernel mode. Okay, so these are the two modes. Okay, that I will illustrate in the form of the diagram. Okay, let us see. So initially all our user task starts with what? User mode. Okay, so always it starts with the user mode. And then whenever it needs some service from the IO devices, now it has to switch to what? Kernel mode. In order to distinguish between these two, which is now every operating system provides one bit, one wire. Again, there is a control signal called mode bit. If our operating system, if a user program is running in the user mode, then our mode bit is equal to 1. Suppose if our user programming is running in the kernel mode, then our mode bit is equal to 0. How to remember this one? Very simple. See, kernel means what? Essential part of the OS. That is essential part of the operating system. Operating system first character O. So kernel mode 0. O 0. This is out. So this is 0. Obviously this one. So that's why our CPU works everything in terms of what? Binary. This is how in ones and zeros. Okay. If it is executing in the user mode, mode bit is equal to 1. If it is executing in the kernel mode, mode bit is equal to 0. When our user program runs in kernel mode, whenever our user program needs some services from the IO devices, our user program has to contact operating system through what? System call. So at that time, our operating system takes these user programs and runs on the IO devices on behalf of the user program. That is called the kernel mode. Okay. Otherwise, our user program is running in the user mode only. Now, initially, our user program starts executing. Okay. User program is executing. So, whenever user program is executing, after some time, either it has to take some input from the input device or it wants to print some data on the output device. So, now it needs some output. So, that means now it executes, it calls system call. That means it calls the system call. Whenever it calls the system call, immediately control will transfer to the control mode, because this user program cannot access IO devices, so it contacts OS kernel. So now kernel will change. Now that means now this is the signal. This signal is called what? This is a user program. Program signal is called what? Trap. Now this will be the trap. That means now it will send trap signal. So when trap signal is done, initially our user program is running in what? User mode. When our user program is running in user mode, mode bit is equal to 1. Now since it is changing to the kernel mode, we need to change this kernel mode bit to what? 1. So mode bit is equal to now 0, kernel mode 0. Now once it changes, now it executes the system call. Executes on IO, okay, or executes IO services or hardware services. Once this service is done, now again the control has to go back to what? Our user program. So now again it will change mode bit, okay, change the mode bit to 1, and again it will goes back and again here continues from where it stopped earlier. Okay, so this is how, okay, but initially here mode bit is equal to what? 0. So this is what? Dual mode operation. So summary, whenever our user program wants, initially when user program is executing, it is in the user mode. In the user mode, this mode bit is equal to 1. And after some time, obviously every user program needs some services from the either input device and output devices. Whenever it needs hardware services, it has to call the kernel through system call. So it will execute the system calls. So once it calls the system, executes call, then that is called trap. So now it has to know kernel changes this mode bit from 1 to 0 and executes that hardware service or execute the system call. After executing, again the control is given back to the user program. So before giving control back to the user program, again changes it to the mode bit is equal to 1 and gives the control back to us. Okay, now this mode bit can be changed only by the kernel, not by the what? User program, because if user program wants, user program only change itself 0 and directly work on the IO devices, then there is no need of operating system. So the mode bit can be changed only by whom? Only by the kernel. And the changing of this executive system call, these are called privileged instructions. Always privileged instructions will be done by only by the kernel. Okay, so hope you understand how dual mode operation. So now in this way, suppose if any user program harms the IO devices or any hardware, so easily we came to know that who is running, okay, which user program is running, okay, that we can easily came to know, because every process is having one ID. How every person is having one name, or how every student is having one roll number. Okay, see, in the same way, every process is having one ID called process ID. Okay, so through the process ID, we can easily came to know that. So in order to distinguish between whether user program is running or our kernel program is running, to distinguish that, we are using this dual mode operation. Hope you people understood. If you have any questions, please write into the comments. Thank you. Thanks for watching.